All right, welcome back. Intro to Technology 1023. We're going to be talking about motherboards today. So, this is going to be quite jam packed with a lot of numbers and concepts. Uh, I would treat this PowerPoint, especially if you're an Alpha State student here, as a reference. Do not try to memorize these. Attempt to understand the concepts as I explain them. But again, do not try to memorize all the numbers that are going to be presented here. It is far more important that you know that these concepts exist, and then you go and Google or reference the numbers that you need if you're doing any type of theoretical calculations. All right. So to start with, a motherboard is a electrical device that takes other electrical devices. All right. It is a PCB with electrical channels that allows for components to talk to each other. So this is the lines that you see on your motherboard. So the way that components talk to each other are through electrical impulses, right? Electrical highs and lows that we talked about through the CPU lecture. Okay, so the major components on the motherboard are off to the right. As you see, I really want to call out VRM and Mosfets because those are going to be the primary things that you need to consider if you are taking a deep dive into motherboards for power for the CPU itself. If you are doing something that is I/O intensive, then your PCIe sockets and slots and PCIe lanes is going to be much more important for that. But relatively speaking, you don't really need that type of detailed knowledge for most things. If you're doing a file server or anything that is GPU intensive or PCIe intensive in terms of 100 gigabit LAN, something like that, then yeah, you're going to need to know what your PCIe lanes are and how your IO MMMU groups are organized and what the chipset's actually doing and so on and so forth. But relatively speaking, you need to understand the power delivery of the system of the motherboard. Okay. All right. CPU sockets. So two primary callouts I have to acknowledge here: LGA and PGA. LGA put the pins on the board itself, the motherboard. Okay. And then PGA is the opposite, where the pins are on the CPU. The reason why this matters is because the pins are the thing that gets RMA'd the most. Okay. So there is no real technical difference between the two. But in terms of what costs the company more, this matters. So if you are MSI and you have a board that you're making for AMD or Intel, a LGA is going to cost you more. And typically the dynamic here is if the CPU is good and on top and popular, the motherboard manufacturer or the board partner is what they're typically called, will take on that extra RMA cost. It's just how it works. When you are down and out, like AMD was 10 years ago, the opposite's going to be true. They're not going to take it because they have negotiating leverage. They're not going to take in extra cost for no reason. Okay, so but generally speaking, from a technical standpoint, there is no difference between the styles. It just comes down to what company has to pay for returns. All right. So CPU socket generations. Again, this is one of those things where you don't need to memorize them. You just need to be aware that they exist. So when you go to spec out a system, you're not trying to have a AM3 CPU on a AM4 motherboard. It's not going to work. Different pin layout. Okay, so we have Intel desktop, Intel server, AMD desktop, and AMD server. Typically speaking, your server and prosumer configurations are going to be either very, very similar or identical. There might be a driver difference, or there might be one or two pins that are going to be a little bit different, but the silicon is the same. So the pin layout is going to be very, very similar as well. Okay, VRMs. This is one of the more important topics for this particular PowerPoint, this particular demonstration. Okay, VRM stands for Voltage Regulator Module. This takes a 12-volt current and converts it to 12.2 or 1.2. All right. So 1.2 is typically, I mean, you can go up a little higher for your CPU. If you give a CPU 12 volts, it will set itself on fire. It's just not designed for that type of voltage. Okay. Phases. We have to talk about marketing at this point. Generally speaking, the more VRM phases in terms of how many actual VRMs that you have, how many VRM phases you have, typically the cleaner the power, the more consistent that power. Okay, so this is helpful for overclocking where you need extremely stable power so you don't accidentally blue screen or crash the system when you're trying to go for a world record. However, in terms of a general use case, it doesn't matter a whole lot unless they're really, really cutting corners and then you're using a top end CPU. But then that's a very strange combination where you're using a very cheap motherboard and a very expensive CPU. But generally speaking, if you get things in the same class of parts, you don't have to worry about this too much. But with that said, some of the other things that you're going to see on the spec sheet and see throughout your little journey through the technology world is this 8 plus 2 or plus anything really. So the 8 stands for 8 phases for VRM phases to the CPU, and then 2 to your RAM. So I have seen up to 4 for RAM, and going in the DDR5, we might see more just because of the higher clocks and the higher power draw. But yeah, 8 plus 2, pretty common. 10 plus 2 is also pretty common. The lower end boards might have a 6 plus 2, something along those lines. But yeah, generally speaking, if you see that, the plus 2 goes to the RAM. Mosfet. I do not have this memorized, and I'm definitely reading off the screen here. MOSFET stands for Metal Oxidized Semiconductor Field Effect Transistor. I'm not going to memorize that for next time either. So MOSFET is used to open the circuit to keep the voltage within the desired range. So MOSFETs are there once the VRM converts that 12 volt to a 1.2, the MOSFET's going to keep it there. Okay, so the MOSFETs are incredibly important as well, and they function a lot like switches. And they also get hot. So one of the things that people look over, especially when they're trying to do a cheap server build, is they'll use old server components and then they'll use consumer fans. And what ends up happening is that your VRMs and MOSFETs end up overheating, and then it lowers the lifespan of the computer or a out and out crash, depending on how bad your airflow is. But generally speaking, MOSFETs are there to keep your voltage within range. So again, this is another one where if you're overclocking, pretty important. So if you have time, watch this video. It goes through everything I just said, except for with animations and graphics, so it's a little bit easier to remember. I don't want a copyright strike. Okay. Pin layouts. Top left, 8-pin CPU power, supplemental power. Okay. 24-pin for your main power that goes to most of the board. All right. The PCB itself, okay, typically speaking, the faster these protocols get, so if we're talking about like PCIe Gen 5, the fact that we've gone up to speeds this fast means that we have to have higher PCB quality. Typically that is done through PCB layers. And as we keep increasing our speed through our PCIe lanes and every other electrical path on the motherboard, these motherboards are going to increasingly get more expensive because it's going to take more time, resources, and engineering to get to the standard and be there consistently. So something to keep in mind, PCB, pretty important. General rule of thumb, more layers is better. PCIe, Peripheral Component Interconnect Express. It replaced the original PCI standard, okay? And it supports 75 watts of power from the slot. So your lower end, and this is common in your GPUs for your workstations, your lower end workstation cards will take no supplemental power. And this is because of the power that is pulled from the PCIe slot, 75 watts worth, well, up to 75 watts. A lot of things don't take that. Okay, this is also part of the reason why you can put in something like a NIC card and you don't have to have power to it. So pretty cool feature. However, generally how these things are engineered is they're based off of PCIe lanes. So physical lanes that go to the CPU. If you're talking about servers, you can get as high as 128 PCIe lanes, which is a ridiculous amount. And then if you're talking consumer, it's anywhere between 20 to 24. Prosumer can be anywhere from 30 to 64. Threadripper Pro is at 128, which is the same as the server market, but uh, again, back to if you're making a server that is very IO dependent and you need those PCIe lanes, then this matters. Until then, if you're just a general consumer, you really don't need it. PCIe standards, again, do not memorize the numbers here. Just understand that there are different standards, and that if you're trying to spec out a system, understand that these exist. More than likely, if you're getting a reasonable system at this point, it's going to be PCIe Gen 3. If it's new, it'll be PCIe Gen 4. And then the coming generations, Intel, the 12th gen has PCIe Gen 5, but AMD is right around the corner, probably the end of the year. That will have PCIe Gen 5 as well. All right, here are your typical PCIe devices. GPUs are common for consumer market at least. Okay, NVMe cards, something that I use quite a bit. And then capture cards, again, something that I use quite a bit, what we're doing right now. All right, fan controllers, depends on how many fans you need, right? So basically what the PCIe standard is, take a bunch of concepts, make a standard so you can physically plug in the device, and then you can communicate directly with the CPU or the chipset for whatever that thing is trying to do. So there's a wide range of things that you can program in with your software and your driver support, but it has to have a standard to connect with, and the PCIe standard is exactly that. Okay, so on this board, here's the PCIe layout. So we have an X1 slot, okay, pretty self-explanatory. X16, 16 PCIe lanes. And that is the longer one here. And on this particular board, it is reinforced. Same thing with that second one. And then you have a PCIe by 8 slot at the bottom. Now, that is the same size as the PCIe Gen 16. The difference is that there is no physical PCIe electrical path to the CPU or the chipset. There's only 8. And part of the reason why this is done is because it's cheaper. The other reason is because you can still plug in X16 devices, and depending on what you're plugging in there, it might not actually need all 16 lanes. And even GPUs up to this point haven't saturated the PCIe Gen 3 by 16. So it was really not that big of a deal up to this point, and we keep getting faster, so it becomes less of a deal. Okay, I/O hub stands for input output. Okay, so this is going to be your USBs. This is going to be your speakers and microphones. This is going to be, some have digital outs like HDMI and a display port, but generally speaking, input output stands for input of data or output of data. Nothing more, nothing less. USB, I'm sure that everyone is used to this by now. Okay, USB is also a standard for communicating with a PC. It is hot swappable, and we have essentially 3 different standards for that. There's USB-A, B, and C. Here are your different speeds for the generations. Okay, recently the USB standard has made this even more complicated because now there's Gen 2 by 2 or Gen 2 by 4, Gen 1 by 4, or Gen 1 by 2, which is direct PCIe lanes to the CPU. Not super awesome for marketing because it's incredibly confusing. Just understand that these are the speeds, and if you ever get to that point where you need a removable device that is that fast, like Thunderbolt, uh, you're going to have to do a little bit of research. Okay. USB formats, I already talked about these. All right. Thunderbolt, made by Intel, uses PCIe lanes. That's why you can get up to 40 megabit or 40 gigabit, sorry, per second, because we're completely bypassing the chipset and going directly to the CPU. Okay, Thunderbolt 1, 20 gigabit, Thunderbolt 2, 20 gigabit, Thunderbolt 3, 40 gigabit. So one of the things that's awesome about Thunderbolt is that it's basically a one cable that does everything. So it does display, it does Ethernet, it does data transfer, right? It does power. That's basically everything that you need. So uh, I have a little Thunderbolt set up in my office where I can plug in one cable and it turns on two monitors, charges the laptop, and I can transfer files if I need to. It's awesome. Expensive, but awesome. Okay, here's some I/O ports and an I/O shield. Chipsets. Traditionally speaking, there was a north bridge and then there was a south bridge. The north bridge handled all the communication between your faster devices, so your GPU, your CPU, and your RAM, typically. Okay. The south bridge handled all the communication between the slower devices. And the reason why you had to separate those out is because the south bridge, the slower devices can be dramatically slower and dramatically different. So maybe that USB 3 device is significantly faster than that old SAS drive. The chipset, the Southbridge chipset, would have to handle that, and that obviously slowed the communication down because there's quite a bit to account for there. Northbridge, less so, right? So it operated a little bit faster. Now, we got to a point where the Northbridge was too far away from the CPU for things to operate at the speed that we wanted them to. So we had to move the Northbridge to the CPU itself. So there is no such thing as a Northbridge anymore, and it's just called the chipset, which traditionally functioned as the Southbridge. So things have really rapidly changed in this little scope here within the last 10 years. Here are your AMD chipsets. Again, this is going to get updated at the end of the year with the new architect and boards. Intel. RAM slots in particular. So you can have one channel per slot. I haven't seen this in a long time. All right. T-topology. This is by far and away the most common. Okay. So this is, unless you're getting a dedicated motherboard for overclocking, it's probably going to be a T-topology RAM slot. All right, daisy chain. Daisy chain is technically a little bit faster than your T-topology. However, you do have timing issues, and then you also have stability issues as well. So it's not particularly great for most things. So T-topology is going to be the better option here, or the best option is one channel per slot, but that's very expensive to implement. Okay, RAM channels, you can have 1 through 8. It is not counting how many RAM sticks there are. It depends on the RAM itself, the channels, the RAM itself, and the actual physical pathing on the motherboard. Okay. So that was a very quick overview of motherboards, and that was a lot to take in. However, like I've said in the past, these are designed to be references. And I mostly want you to understand that these things exist, and then you can go find your reference or Google it to make sure that you actually understand it for whatever you're trying to do. That could be an analytical paper, or it could be building your own system. So With that said, that's all I got for this one. We have quite a few more of the hardware presentations to go through, so we're going to be doing that for a little while. And then other than that, that's going to do it for this one in the motherboard section, and I'll see you in the next one.